pues vamos a dar. Oh, okay. I'll introduce you. You're going to talk in
English. I will just speak in
okay.
English. Yeah.
Please don't talk in English. I'll introduce me in English. We're going to have we have a pleasure today of having Professor Yann Mambrini giving us talk on gravitational production from inflation to primordial black holes with cheap world systems. Yann Mambrini completed his undergraduate studies at Rosales and his PhD at Montpellier. And then he did two postdocs, one in Madrid and one at Desi, as I understand. And he currently serves as a research director at the French CNRS, Centre National de Recherche Scientifique, in the Avila laboratory at the University of Paris-Saclay. His research primarily centers on particle physics and fundamental interactions from supergravity to gravity-type theories. He focuses, as you can see from the title of his talk, on cosmological implications, especially within the study of dark matter. He has received the Prix d'Examen Scientifique from the National Research Council in 2010, 2014, and 2018. And apart from his academic pursuits, he's deeply intrigued by the concept of time, ranging from its measurements to its fundamental nature and the historical evolution of ideas in physics. He has authored several well-received French books on three subjects: Histoire du temps, le cycle de révolution scientifique, sorry my accent, Newton à la plage, and La Nouvelle Physique. But also, alongside his scholarly endeavors, Yann shares his passion for magic. So some of you know about this, but reading illusions into discussions about time and the mysteries of the universe in shows tailored for the general public. So today he's going to look at the most different, just like not magic, but gravitational production. And please, Yann.
Thank you. Thank you for the nice introduction. Thank you for the invitation. So it's always nice. Hablo un poquito de español, pero prefiero hacerlo en inglés, okay? Por mi culpa. Thank you a lot for the invitation. My second time in Mexico, in Mexico City. So very nice city. Always, I'm amazed of the dynamic of the laboratory and of the department. Yeah. Normally in seminar in IJCLab it's not like this. We have very few people. So I will try to during this talk, which I say I hope it will. Okay. So I will try to explain you. I hope in a didactical way the mechanism of production of particles in the early universe, but using the simplest tool we can have, the simplest mediator we can have, which is gravity. So of course, it will not be a quantum theory of gravity because we don't have a quantum theory of gravity, but it's a kind of an effective quantum theory of gravity because we will always be at scale below M Planck. So we can always have considered the metric and the graviton as a perturbation of the metric. So we can treat the graviton as a classical field, if you want, or the general relativity with classical fields, and we can still make some computations. And as you will see, it's related with Hawking radiation, with Hawking Gibbons temperature, of this kind of thing, of Unruh effect, De Sitter effect, all we can imagine. Second thing I want to tell you, the University Paris-Saclay is a new university nowadays. So before there was Paris-Saclay, Paris-Orsay. Maybe some of you heard about Orsay. So now it's finished. We all gathered one university, which is Paris-Saclay. It's all what is south of Paris. The three University of Paris. This one is Paris South. So I want to make the publicity, but I will skip the publicity for the book Particles in Dark Universe. Okay, if you want to have some details about the calculation, you will see. The book is available in the office of Marcos, right? And in the library also? Yes. In the library, exactly. So my talk will be based on several work we did recently, some of them with Marcos. So also, if you have some question, you can always ask to Marcos in the office if you want some details. When I'm not here, I'm still here next week, so we can always discuss also next week. This work is quite recent because treating PBH, there was a revival on primordial black hole recently. Mainly, of course, because of the discovery of the gravitational waves, not primordial gravitational waves, but binaries, gravitational waves produced by binaries. And so, yeah, I would say the physics is kind of now much more active and dynamic on these fields. Even on the part of the early universe and gravitational production in the early universe, it's also quite old because the idea is coming from Ford, Parker, even Schrödinger, if you go back in time, how changing the metric can produce quanta. Okay, these are the things, how changing metric produce quanta. That's just the game that we played in 1 hour. So you change the metric around the black hole, that's what we call the Hawking radiation, everybody know it, and you also change the metric during inflation, okay, which is the interstellar space. So as you will see, both produce an horizon. If you have an horizon, you produce quanta. That's the main idea. If you understand that, the rest is many calculation. So also for the students and the postdoc who are part of all this work, so there is my ex-PhD student, which is now in München since 2 weeks, in fact, Eso Dejlo, which was a student of Carlos Munoz in Madrid, and which is with me, and another position now, and my PhD student Mathieu Gross, my ex-PhD student Matthias, which is now at DESY, and my postdoc Jake, and Riajoul, with who I work also, which is functional. So it's a list of a majority of them contributed to the talk you will see. So I have given the title of my talk, Two Chief Systems of the World, or two major chief systems of the world, which is the title of the book of Galileo, where I compare, of course, two kinds of world, which is the non-living world, I would say, and the Galileo world, Copernic world. So I will try to convince you that that if you have one world, you should have the other world also. Okay, like Nolem and Galileo are two kind of vision of the same world, depending on your point of view. If you produce particles from gravity in the inflationary era, you should also produce to the black hole because it's the same kind of production, same kind of mechanism. So if you have one, you have the other one. We know black hole exists. We know at least the dark energy exists. So universe exists in an accelerating expansion. So every time you have acceleration, you have production of quanta, because we'll see. So both acceleration you have Schwarzschild radius, you have the de Sitter horizon, both horizons produce particles. So if you have one, you have the other one. So we'll try to compare the two ways to produce particles through deforming the metric. So the plan is very easy. So PBH can read the universe, can populate dark matter, kinetogenesis, I will say, and generate gravitational waves. GGW is for gravitational waves. And Inflaton can do the same just through gravity. So all what I will show you, more or less, it means it's the minimal amount of things you can produce. Right? Of course, you can now go to BSM physics. You can add supersymmetry. You can add another fifth force, SO10, SU5, whatever you want. You can go right on neutrino. You can do whatever you want. But all what I will show you is just with standard model plus gravity. That's all. I will not add anything more than that. Okay? Just to show that just with that, we can solve, I would say, the main problem or the main question you have about the universe. So just to make some generalities between the inflaton and the primordial black hole. So I will try to explain first what is an inflaton. An inflaton is a homogeneous field, classical field. Okay, that's how we consider first classical. After I will I will look at the perturbation on what I say. But nowadays, it's just we suppose it's classical field, so it's the same everywhere, which is oscillating. Okay, so it does not depend on the position, depend on your time. And it transfers its energy through its oscillation. Okay, it's like the Bose-Einstein condensate. If you want to see the analogy in quantum mechanics, let's thinking as a Bose-Einstein condensate. I decrease my temperature to 0. I have collective effect, and I don't have a lot of particles. I just have one particle, and all oscillate collectively. It's equivalent to having an homogeneous field. Okay, so it's just a field which oscillates in the universe, and the oscillation of the field transfers its energy to quanta. For the black hole, of course, it's the decay of a black hole, evaporation, its energy to quanta. So if you just want to understand where all is coming from, so I will do level by level. So the first level for everybody, of course, here I think is aware about that. So if you want to understand where is coming this quanta, this can be fluctuations, or can mean condensates, or whatever you want. G mu nu equal T mu over m Planck square, and the energy momentum tensor, I write it as a potential. Let's suppose it's just a potential, it doesn't depend on time. So it's just a density constant. So I just suppose a quadratic potential, but call it rho chi, density of energy, V of chi, potential, whatever you want. So it's a T mu nu. I just take the time part, which is the potential density of energy, 0, 0 part, just to show you what's coming from. So if I have a transformation of the metric, I will produce quanta and vice versa. Okay, so modifying my metric, putting some acceleration here, you will see, I will generate naturally a quanta, okay, a vacuum expansion value if you want, or constant density, or some fluctuations also of the fields, as you will see. So playing with my metric will produce me quanta. This is, of course, the generic idea. Now, if you want to go a little bit more deep in the equations, so if I write my metric, okay, I know that I have two kinds of potential I can write in general relativity. I can write, of course, potential, which is a Schwarzschild potential, okay, which is with a Schwarzschild radius, it's a potential 1 over r. Or I can have a potential which is in r squared, okay, and of course, this is the what we call cosmological constant or inflationary phases, whatever you want, is a de Sitter space. So I have a Schwarzschild metric, I have a de Sitter metric. This is the two metric we know. And of course, depending on how you write it, you can always play on defining a time, co-moving time, the time you want. You can always write the metric in a Riegler space or in de Sitter space. You can play with that. And you see that in one case, you can always know the coordinates. You can see that you can define, in fact, radius, Schwarzschild radius, okay, an horizon, I will call H for an horizon, the horizon for Schwarzschilds, which is defined by m Planck square over m black hole, okay, which is Schwarzschild radius, okay, which is just a gm divided by 4 pi. And if you play with a de Sitter space, you can have the same kind of horizon, okay, which is the de Sitter horizon, which is given by the cosmological constants. What it means more or less, which is in space coordinate and time coordinate, it means more or less that here I'm inside the black hole, and all what is above the Schwarzschild radius, I don't have information coming from the space which is outside of the Schwarzschild radius. So yes, it's a Riegler space, so I suppose I'm inside the black hole. I have the radius of Schwarzschild, and out of my radius, in fact, I don't have communication because the information cannot come to me. And in the case of de Sitter space, of course, I'm here. I have my de Sitter horizon, my horizon increasing, and other points which are beyond the horizon will not reach me. Okay? So whatever your point of view it is, you have an horizon inside the black hole or de Sitter which is expanding. It's just tricking with equations, but as I said, at the end, the same things. And you do like Hawking did, or like Bunch Davis did, and Ford and Parker, you just do Bogoliubov transformations, which means that I have a field. Of course, I write it roughly, but you have a lot of 2 pi that I don't write. So you have positive frequency, negative frequencies, some positive frequency, negative frequency can be interpreted as particle and antiparticle if you want. And so I can create, in fact, doing a Bogoliubov transformation, I can compute my amount of particle created from beta equal to 0. If I accelerate my space, I have beta which is not 0, which would be created by my acceleration of the space. And the shape of beta, you notice it, is the same shape than the Boltzmann distribution, if you want, or Fermi-Dirac or Bose-Einstein, whatever you want. And so I can define the temperature. So H is my horizon, which is this one or this one. So I can define the temperature, which is m Planck square over m black hole, which is the Hawking temperature. So this is the paper of Hawking of 72. Or I can define, which is H lambda. So H lambda over 2, or 2 pi if it is a de Sitter space, okay? So to explain to students, if people doesn't do general relativity, it's just coming from the fact that when I'm running in how you say in English when you make sport, this thing which is running like this to make sports. How you call it?
A treadmill.
Treadmill. Treadmill? Okay. If you're on a treadmill, of course, or in the airport where you have the same kind of things, okay? So if the treadmill is not walking, everybody go in the same direction. If I switch on my treadmill, in fact, suppose it's 10 kilometers per hour, the treadmill, all people which is walking less than 10 kilometers per hour will go on the other direction, will go on the right? So at the beginning, I will see everybody going to the left. If I switch on, which means I expand my universe, so the treadmill represents my universe expanding. If I expand my universe by acceleration, I will have some of the people, the slower one, will begin to go on the right, okay? This is antiparticle, okay? So if you want to interpret particle-antiparticle creation in the horizon of a black hole, that's exactly that, okay? The particle which is slower go to the other direction, negative frequency here, so negative frequency. The negative frequency corresponds to antiparticle. So if I switch on my expansion rate, I will create antiparticle, okay? I mean, you can interpret it whatever you want, but that's the mechanics. So, which is fundamental at the end, it is that the vacuum, in fact, state of a field depends on the motion of the observer. Okay, that's something fundamental. It's coming when all this happened because I have included general relativity in my equation, quantum field theory equation, right? Which means the number of particles is observer dependent, right? So I don't see the same particle depending on how I move. I have one photon. If I move on a certain framework, the photon disappears. So it's strange. I don't say it's true. Huh? We never saw Hawking radiation. I mean, all what I tell has not been observed. Okay, so it's just theory. Huh? You don't have to take it as granted. Huh? We don't know it is, but this is what the equation gives when I just take QFT and I put in my metric general relativity. That's what I got. So my number of particles depend on the observer, not the frequency, not the this we know of course. If you have frequency change, this is number of quanta, right? The number of particles depend on whatever. If you have one photon, there is a rest frame where the photon disappears. So this is not new. If you look at this, so yeah, just to compute it, of course, if I have a temperature, okay, I can compute the density of particles. So in the case of black hole, it will be the density of the black hole I have in the universe multiplied by the temperature or the mass, depending on if the mass is above or below the temperature of the black hole. You will see that. But my density of energy of a particle will be how many black hole I have per meter cube, multiplied by my temperature of my black hole, giving my density of energy. And in the case of Hawking of a de Sitter space, it's h to the 4. Okay, which is quite easy to understand. Is just think like a space in an equilibrium, right? If I have a temperature which is h, I have rho which is h T4, it's h4, right? Think like this. Okay, so if I have an universe which has a cosmological constant, okay, or inflationary space is the same in inflation. If I have a Hubble rate which is constant, which means I'm accelerating, of course, if I stay here, I'm a universe which is doing like this. I see appearing quanta, okay, with a density which is T to the 4, and my temperature, as I showed you before, by Bogubov transformation, is a Hubble rate. So I'm feeling as if I'm living in a thermal bath of particles just because the universe expands. Is the famous G mu nu get kappa T mu nu. I have to transform my geometry into quantum. Okay? So that's what it is. So this is not a new idea, to be honest. Schrödinger was the first to got the idea because he applied general relativity to quantum theory, not quantum field theory, because it was in 1939, so it was before QFT. So he just took his equation. You can do an exercise. You do the Schrödinger equation, and you change the metric. And you take the Minkowski metric. You take just the metric of general relativity. You take G mu nu with the special part, which depend on time. And you can make it. You will see that you generate particle with negative energy, okay, which corresponds to the Bogoliubov transformation in QFT. This corresponds to negative energy. It's almost the time of Dirac. Also, Dirac was a little bit before, so it was still discussing about what is antiparticle. It was after discovery of the positron. So he said that it was alarming in this case. This is from his original paper. Is alarming phenomena, he called it, which would be probably caused by accelerated expansion. Okay, so he said that they may play an important part in the critical period of cosmology when expansion changes to contraction or vice versa. So it was, of course, it was after the de Sitter work, after the Hubble discovery of 1929. But we know universe was in expansion, but not accelerating. So it was not de Sitter space. At this time, there was no acceleration. Okay, h was not constant. So it was the case that he proposed that why not, if you have an acceleration state, so if h is constant, you can generate negative energy. So he called it alarming phenomena because, in fact, you will create antiparticles. You have a particle, will create antiparticle, and all will annihilate, and universe can disappear. Or you can have photon who will go backward. Okay, you have negative frequency, and it was corresponding to photon going backward. Okay, or the photon will go there and bounce toward you. So if you expand fast, the photon go and bounce above you. Of course, it was just with Schrödinger equation. When you QFT with multiple particles, it's not happening. This is a paradox of just one particle. But it's interesting to read the paper because it's more or less what we do in QFT. So, but after there was a lot of work about that. Schrödinger of force effect, which is exactly the same. Schrödinger effect is exactly what I'm doing now, okay, but for electromagnetism. Schrödinger effect is just that I have an electromagnetic field. If I give acceleration, which means if I stretch my electromagnetic field with acceleration, not smoothly, but accelerating like this, from E2 to E1, I will create particles. Schrödinger effect has not been observed yet. Okay, so still it's theory, but Stuttgart effect is exactly what we do for gravity, for electromagnetism. Okay, for QED, but it's exactly the same things. Unruh effect, okay, that we know also. So Unruh effect we cannot observe because Unruh effect with the value of cosmological constant we have now, we should observe like 10 to minus 41 particle appearing every century. So we never see this appearing now, but Unruh effect is compute how many particles should appear. You can make the computation by hand, just you know this temperature here, this density, you know the cosmological constant, so you can even do now the exercise, how many particles is produced here per second per centimeter cube. Through the expansion of cosmological constant, you can compute, I think, 10 to minus 41, something like that. So you don't observe it, but it's predicted by the expansion rate of universe. And of course, after that, what is bunch Davis for Parker works. This is from the 70s, so 4065, Parker 72, 80, so 82. So this is Parker just apply these phenomena to the inflationary model. Okay, when inflation appear, Parker proposed to explain how particles were created in the early universe because it was a part of inflation. So Parker is just after the work of Guth, Steinhardt, and Starobinsky. Okay, so after this little introduction, all the rest is just poetry, is calculation. So if you understood that, you can leave the room, okay, you can say if you want, but all was done here. After, you just have to compute. So you compute beta, Bogoliubov coefficients, you compute the scattering process, you compute things, but it's just things you have to do. So let's compare these two horizons. I told you you have a Schwarzschild horizon for black hole and you have the De Sitter horizon for space and expansion. So let's compare these two strange particles, or not particles, not strange objects in space, which interact gravitationally. So for the density evolution, so density of black hole is quite easy in universe because it's diluting. So you have several black hole, universe expand. So my density of black hole decrease as the scale factor -3. I just dilute. So this is my universe expand. I dilute my black hole. So my energy density of black hole decrease, of course, in time, but like A-3. In the case of inflaton, it's a little bit more complex because inflaton is a field where the pressure. Black hole has no pressure, okay? It's a dust, it's a particle, a big particle, it's a black hole, doesn't move, okay? So phi is a field where a pressure. Okay, having a pressure, okay, means that it can evolve differently. For instance, if I have a potential which is lambda pi to the square, which is a dust, we call it a dust, massive field, you can compute easily that it decreases, it's diluted exactly as a black hole, it's a dust, it's a matter field. So it can be seen as a heavy particle in the universe expanding. So it's M3. But if you have a potential like 5 to the 4, as you notice, if it is 5 to the 4 means I don't have dimension. You understand that it's 5 to the square, it means to have dimension 4, I need to add mass square. So you have a mass scale. So it's easy to understand if I have a mass scale, it's like a particle with a mass. If it is lambda 5 to the 4, lambda has no dimension. I don't have energy scale in my model. So it's like radiation. Okay, I'm just diluted again with 4. Okay, so my energy is diluted and my number density is diluted. So I'm diluted as M-4. So the main point is that inflatons have a tendency to be diluted more than the black hole, which means you understand quite well that during the time of universe, black hole will dominate after a while, you will see it. Because black hole, in fact, dilute less than inflaton fields, except if it is a quadratic potential, where both dilute the same. For the lifetime, we can more or less consider the inflaton as a particle, and for people who compute lifetime, the lifetime of a particle is proportional to the mass of the particle. Be careful also, because it's a field which oscillates, but the frequency slow down. In fact, it's not exactly the mass, it's the frequency of the oscillation. Don't forget, it's not a particle, it's a classical field. But with the computation, we can make some confusion sometimes, but the mass is a frequency. So I have a frequency, and my lifetime depends on my frequency, right? But my frequency also decreases with time. So my lifetime decreases with time, okay? So I'm decaying first a lot, and then less and less, okay? The black hole is the opposite. The lifetime is inversely proportional to the mass of the black hole cube. The lighter it is, the more decay, and as the black hole is losing its mass, okay, is increasing his decay rate, so is decreasing the lifetime. So it's like an explosion, right? So it's at the lifetime decrease, boom, and explodes. Okay, so with time, the black hole will increase its decay rate, and the inflaton will decrease the decay rate. Okay, so it's two opposite behavior. Gravitational production, you understand what I said before. For both cases, it's more or less the same. In one case, it will be the exchange of graviton, okay, which is a quantum field perturbation of the metric. In other case, it will be the Hawking radiation. For the spectrum, it can be interesting. So the spectrum of what you produce from a black hole is a thermal spectrum. Not exactly thermal because you have some gray body factors appearing here, and you have the effect of a mass before exploding, which grow very fast. So you have some non-perturbative effects. So it's not exactly a thermal spectrum, but it's quite similar to a thermal spectrum. Wherever, of course, the spectrum of an inflaton field is redshifting. So I remind you, so I have frequency, but my frequency is redshifting with time. So my spectrum is much more complex and redshifts much differently with the scale factor of time. Okay, and when they decay, in the case of inflaton, in fact, they decay when the density is larger, so it is just at the end of inflation. So I have a phase of inflation, okay, and then my inflaton begin to release all the energy of inflation into particles. So this is where it is stronger, okay, after it's begin to be diluted. So it will release all the most of its energy at the end of inflation, which is the beginning of what we call the reeking phase, when you give the energy to the back. And of course, for a black hole, when it evaporates, this is an explosion. If you want, this is why you give all its energy. And what is the frequency? It's good to give some numbers also. So what is the frequency you expect if you have a field which is quite massive, the energy of an inflation? What kind of frequency it's left now, okay? If you release it in gravitational waves, for instance, what kind of frequency you expect? For experimentalists is important. Very easy to compute. The frequency is the energy at the end of inflation. So just to give you an idea, the energy at the end of inflation is around 10 to the 12, 10 to the 13 GeV. Okay, just to give you an idea. So it's around the gut scale, if you want some idea. So the inflationary scale is around this scale. Okay? So 10 to, from 10 to the 13 to 10 to 15 GeV. I don't go into details. It will give you some idea of the value you expect. So if I say 10 to 13 GeV, the redshift between S0 and end of inflation, if I take 10 to 13 GeV, nowadays it's 10 to minus 13 GeV, right? The temperature T0. Okay, so it's a redshift of more or less 28. Okay, so 28 minus 10 to minus 13, 10 to 13 minus 28 is give me 10 to minus 15 GeV. Okay, 10 to minus 15 GeV give me 10 to the 10 Hertz. Okay, 25 to pass from Hertz to GeV. Oh, not too fast. 10 to 25 Hertz is 1 GeV. Okay, so it give me 10 to the 10 Hertz. Okay, so I expect whatever I talk about gravitational waves, but it's not important. Whatever is happening nowadays, what is left is 10 to the 10 Hertz, which is larger. Now, you know, the gravitational wave we measure now is 1 Hertz or 0.1 Hertz or 10 to minus 2 Hertz. So 10 to the 10 gravitational waves. And what is funny, and nothing to do with that, but the frequency nowadays of a black hole is the same. So there is no relation between both of them. I don't see, I try to see during some months why it's exactly the same numbers. I don't know if there is something hidden there. But a black hole of 1 gram, okay, you can compute the temperature. Temperature is m Planck squared divided by the mass of black hole. Okay, so m Planck is 10 to 18 more or less. Mass of black hole 1 gram means 10 to the 5 Planck mass. So 10 to the 5, so 10 to 18 minus 5 give me 10 to 13. You can make the calculation. So you expect nowadays also 10 to 13 Hertz. So more or less same range of parameter, right? So if a black hole decay, more or less, evaporates in the early universe, so 1 gram black hole, just keep in mind, if I have a 1 gram black hole, it will release the same kind of frequency than an inflaton at the end of inflation, 10 to 13 GeV. Right? 10 to 13 GeV, it's exactly the same than 1 gram black hole. Keep that in head. 1 gram black hole, Hawking temperature is 10 to 13 GeV. So end of inflation, 10 to 13 GeV. So 10 to 13 GeV is 1 gram black hole or is an inflaton. Same. So inflation can be done, for instance, by 1 gram black hole. So how it evolved now during the time? So you had the inflationary phase, so the universe has been phi was constant, okay, so inflationary was going from a Hubble rate which was constant, quite large, poof, okay, and then the inflaton began to oscillate and you're releasing his all his energy through the oscillation. So I will take the case k equal 2, which corresponds to quadratic case, m phi square, which is easiest one. It's a dust, it's like a particle, so it's just, losing his energy and diluting as Ml3, and then it's decaying, he has a lifetime. When it's decaying, all his energy is released in the radiation, I call air the radiation. Radiation means Higgs, photon, W, top, quark, whatever you want. Okay, this is what's called the reheating. Okay, reheating is when the inflaton decay, all the energy of the inflation, which has been diluted by expansion, is released on the radiation, and you begin your story that we know now. I mean, BBN, CMB, blah, 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 all is coming from that. For the black hole, you see, it's not exactly the same, so it is evolving the same. What we call beta is the convention. Beta is the ratio of the density of black hole compared to the inflaton field, okay, or the dominant field in the universe. Beta is the proportion of black hole compared to inflaton. Of course, you have less, okay, so it's less than 1, but it's a parameter. Some people compute beta. It's not easy to compute beta. I will show you how you compute beta. It's not so easy. You can compute inhomogeneities coming from the fact you have some inhomogeneities, and inhomogeneities contract from black hole. So, of course, if in this case, you can think black hole does not play any role in my story because it's always subdominant, it's decaying here. Okay, you don't see anything there. So I can forget this scenario. But of course, depending on the mass, if the black hole is heavier, the lifetime is longer. So it can, for instance, decay after. So if I have a black hole would decay after the inflaton, so depending on the ratio between the mass of inflaton and my mass of black hole, I can make the reheating from the black hole, not from the inflaton. Okay, we call it PDH reheating. Okay, so you can have inflaton reheating or PDH reheating. Or of course, the other possibility where black hole can be important, it is that if my inflaton, I told you, has a pressure. If my inflaton has a pressure, it will redshift like A-4, for instance, if it is a gas, as a gas particle, or if it is, as I will discuss after, if you fragment it. So if it is a gas, you see that it redshifts much more than A-3, and so the PDH can dominate the universe. So there is different ways where the PBH can dominate the universe over the inflaton and can produce the reheating. Okay? Yes.
Do you always need an inflaton, or can you make it work just with primordial black?
No, you need inflaton, you need inflation. Primordial black hole has not the characteristic of having giving you constant cosmological, other rates. Okay? So this is not possible. So you will need something to make inflation. Yeah.
Thank you.
Yeah, no, you're welcome. Of course, other possibility, it is beta is very small, of course. I don't have PBH because I don't produce them. This is super active field of research, computing beta. Okay, that's not easy. Okay, computing, I have a gas of particle, I have inhomogeneities, how many black holes are produced? That's a lot of people work on that. It's quite recent. Yeah, I would say since 2 years or 3 years, this field is super active and much more people work on that and it's going very fast. So this is a summary. So I have a black hole, right, at evaporation time. EV means evaporation. INS means when it's produced, when producing of the black hole. So it just, I have a fraction of my inflaton field as a production, and I'm redshifting at M3. And this number, you don't care, but you can compute it. It's not complicated. It depends on the mass of black hole. Okay? And for the inflation, of course, is a classical M3. I consider now quadratic. So you can compute the beta above which the black hole dominates, right? It's easy. For each mass, I have a value of beta, which is critical, where the PBH dominates. To give you an idea, for instance, 10 to the 4 black hole mass, okay, if I have beta more than 10 to minus 9, I dominate all what I told you. Right? So I know for which value of beta, for each mass of black hole, I know which value of beta I need, so that it's not the inflaton will give me the story of universe, it's the black hole will give me the story of universe. Okay? So this is a region which eliminates where you should take care of black hole or not. Okay, for different equation of state. So W is what we call an equation of state for phi. Okay, as I say, depending on the pressure. So now you saw the generality. Let's apply it to what we call reheating. Reheating means when you produce photon. Okay, us. Okay, not dark matter, not the right hand view, but us. So for that, I need to compute the famous beta function I told you. Now I will tell you how we compute it. It's quite easy. Suppose you have some inhomogeneities in the universe. Okay. And you need this inhomogeneity to be more than a critical density, okay, such that the black hole collapse. I mean, the matter inside this horizon collapses into the black hole, right? It's a critical density where you begin to have the collapse. This is around 1, okay? It's a little bit more than 1. It depends on the model, but you can compute what is for each equation of states. Is it a gas of particle? If it is inflaton, whatever. It's a function of the pressure, of course. You understand quite well, if I don't have pressure, I don't have black hole, right? I need some pressure to form a black hole, right? The more I have pressure, the easier it's to form a black hole. Okay, so it depends on the pressure of my gas. So what is the fraction beta? It is just this little part. Yes, is delta here, right? Probability of having delta and I should lie in this region above delta critical, and this is my portion of space which has been contracted into black holes. That's not complicated, this is how you compute it. But as you noticed, my black hole go like a to the 3, minus 3. My phi go like a minus 3, 1 plus w, w being my equation of state. So for 0, of course, is a dust, so 3, but for 1/3, it's minus 4. So you see that my ratio of black hole on phi go like beta a 3w, which is always positive, which means we know that black hole should dominate after a while if it does not decay before. So that's what I told you. We know that black hole will dominate the universe if it's not decaying before. Okay, so what's happening? So I have a delta critical, I have an homogeneity here, another one here. This is the size of my horizon. I will let the time passing by. During the time when my horizon will catch the perturbation, blam, collapse into a black hole. So we'll have a black hole. Time is passing. Some 10 to minus 20 seconds is passing. My horizon catch another perturbation which is larger. I will form a larger black hole because all the matter inside my horizon collapse into a black hole, and this horizon is larger than this one. So if I form black hole later in time, my black hole will be larger, right? If I wait longer, my black hole will be larger. So my black hole is formed larger and larger. So if I give you some numbers, just to give you some numbers, the mass of the horizon, which is given just by 4/3 of pi multiplied by my horizon cube multiplied by my density, very easy, okay? So a black hole, for instance, of 1 gram is formed at 10 to minus 38 seconds, right? Quite early. 10 to 16 gram, which is stable black hole, 10 to 16 gram, if I correspond to dark matter black hole, is formed at 10 to minus 23 seconds. And the black hole, which is solar mass, is formed at 10 to minus 6 seconds, so just a little bit before the Big Bang. Okay. So typically, in fact, so the mass you see, and you can have all the range of mass for 1 gram to solar mass, and if you form a galaxy side, it's just before the CNB. Okay, so black hole collapse more or less before the Big Bang. Before the CNB, you have the size of a cluster of galaxies. Of course, they are unstable. Okay, so you can compute the lifetime from the working radiation, as I told you, 10 to 13 GeV for 1 gram. This, you can remember these numbers. And if you use number of the lifetime, okay, so it's more or less 10 to 17 seconds for 10 to 15 gram. Okay, so 10 to 17 seconds is the lifetime of the universe, right? So the lifetime of a stable black hole is 10 to 15 gram, right? So 10 to 15 gram is formed at 10 to minus 23 seconds and is stable nowadays. Okay? So just to give you some idea of mass of black hole, 1 gram is a butterfly, it's formed at 10 to minus 38 seconds. The universe was 10 to 15 GeV for the temperature. You just suppose instantaneous heating. So, and its lifetime is 10 to minus 28 seconds. A black hole of the Eiffel Tower mass, which is 10 to 9 gram, decay just before BBN. Okay, so between 1 gram and 10 to 9 gram, you are before BBN. Asteroid is the lifetime of it can be dark matter, the lifetime of universe is decaying nowadays. And as I say, so at 10 to minus 5 seconds, you form a sun, more solar mass, more or less, and you form the universe more or less at equality between matter and radiation. This is the proof. Okay. So I will concentrate now just on this black hole between 1 gram and 10 to 9 gram, which is the one which are there during the inflation, during the rating phase within inflaton. Okay, so it's good to have some numbers of mass of black hole. So easy to solve after just numerics. To solve is easy. I have an equation of motion for phi, an equation of motion for my black hole, and an equation of motion for my radiation, which receive energy from my inflaton and from my black hole, because inflaton decay and black hole decay. So a system of 3 equations. Okay, it's first order. I think you can do by hand. It's very not complicated to do. And so 3 system of equation, a differential equation. Of course, you have H, which is rho square, rho phi square, plus rho BH square, plus rho radiation square. Okay, because H is the Hubble rate. So you saw it's 4 equations, in fact, because you have the Hubble equation also, the Friedmann equation also. So you see, so you have my phi will decrease. For instance, I take a potential phi to the 4. My phi go m-4, my black hole m-3. I transfer energy first from the phi, then I transfer energy to the radiation from the black hole, then decay, I have my radiation, all right? You see what's happening? It's not complicated. My phi transfer energy to the radiation, my black hole transfer energy to the radiation, and then both decay, and you have the story of universe. Okay. So I can give you some numbers also, just to give you some numbers of which kind of numbers you wait for the reading. For the width of a black hole, for instance, don't forget, is increasing with time because the mass decrease. The width of the inflaton field is decreasing with time because my density decreased. Okay, so the phi width is at the big efficiently at the beginning, the PBH is at the end. Okay, so both does not act at the same moment. And of course, the PBH can dominate the energy budget of universe, as I show you. And if I give some numbers, for instance, if I have a rating temperature of 10 to the 11 GeV, it corresponds to 1 gram black hole or Yukawa coupling, because it's decaying through Yukawa coupling, for instance. I suppose it's a Yukawa coupling for the inflaton, just to be simple. So for Yukawa coupling of 10 to minus 5, it gives me a rating temperature of 10 to the 11. It corresponds to a black hole of 1 gram. And the black hole of 10 to 6 gram corresponds to Yukawa of 10 to minus 17 or a rating temperature of 100 milli. So you can range all the parameter space, you see, from 10 to the 6 gram to 1 gram. You see that you can have, or 10 to the 9 gram if you want to 1 gram. You go from the MeV to 10 to the 13 GeV. So you have all the range of parameter space for black hole mass or for Yukawa. You can have all what you want. Okay? So which means a PBH mass of 1 gram may dominate over the inflaton if rating is below 10 to the 11 GeV. So if I give you some numbers of rating temperature you expect, for instance, rating temperature of Yukawa, as I said, 10 to minus 4, give you 10 to 7 GeV, okay? And if I look at 1 gram black hole, give me 10 to the 6 GeV. So you see it's quite equivalent. Huh? So all is quite equivalent. As I say, it's coming from the fact that 1 gram Hawking temperature of 1 gram is the same than the mass of the inflaton. So you understand quite well that the 1 gram black hole, in fact, will give kind of the same thing than an inflaton. Okay, 1 gram black hole is the same as inflaton, more or less. Rating, and for all the rest, it will be the same as you understand. The mechanism is different, the division is different, the lifetime is different, but at the end, the numbers are the same. So if you compare, for instance, just the full line, the dashed line is for another parameter space, just see the full line, the blue is inflaton, this is numerics, the red is the radiation, and then you can see that if I have the black hole in green, okay, so I change my radiation, which was red here, you see red, now it's going a little bit up, okay, because the black hole begins to dominate here. The black hole dominates, so the temperature go up, and then it follows the classical line. So just having two systems of transfer of energy, always gravitationally, you can see that you can have the two systems. The same, you can make a plot. This is the scale factor, which means the time. This is the CMB, and this is the end of inflation. So you have inflaton domination, PBH domination, and radiation domination. Okay, so you have all the phase which can exist. So of course, you can also play the role with dark matter. So I told you I can produce radiation, but I can also produce dark matter. You do exactly the same exercise. You just add one equation for dark matter. You say, in fact, my black hole decay to the dark matter, and just add one equation, and you play the same game. So you can compute the radical abundance produced through the fact that BPH has decayed to dark matter. Okay, so the same, just little subtleties here. It is that if the mass of dark matter is above the Hawking temperature, and you have an exponential suppression, the Hawking temperature, as you know, is increasing because my width is increasing with time of black hole. So my temperature of black hole increase with time. Just before explosion, it reaches an infinite value. So you see that if my temperature, in fact, when the temperature reaches the mass of my dark matter, I will produce it. So I produce my dark matter in this region here. So you can have heavy dark matter, much heavier than temperature of black hole, but you have to wait that the black hole has sufficiently decayed, so sufficiently hot, so that you can produce the dark matter. If not, it is exponentially suppressed. Okay? So if the mass is below, you produce evidently, obviously, because the mass is below the temperature of the black hole. If it is above, you can still produce it, but you have to wait. The temperature of the black hole is sufficiently hot, so you produce it. So if you do some numbers, so the same. So it depends, of course, on beta, which is how many black holes I have. Okay, more or less, beta is my number of black holes that I have at the beginning. But the dependence on the mass of black hole or dark matter, of course, are not the same if I am below the Hawking temperature or above the Hawking temperature. But this is just solving the Boltzmann equation combined with the Hawking equations is super easy. So this region is allowed for that. Yeah.
I got a question. There are some people who think that actually primordial black holes could count for some amount of dark matter.
Dark matter, exactly.
So
so I have stopped here because this is the decay of BBN, right? After the decay after BBN. You can have black holes. You have a region blind where you cannot have black hole in a sense because they decay during BBN, so they change a lot the story we know. From BBN to now, we know the story. But if they decay after 10 to the 17 second, which is a black hole of 10 to 15 grams, they can be black matter candidates. Except that only a small region is allowed, which is between 10 to 17 grams and 10 to 19 grams of black hole, right? This little region is not excluded because this kind of object can be excluded by microlensing, by other kind of macho research. So all the mass, in fact, for different research, you can see the plot, is excluding. Not excluding, but you say you can compute the fraction of black hole which can be the dark matter, right? So, or if you want all the primordial black hole to be dark matter, it's only 10 to 17 grams, 10 to 19 grams. This region, we could not yet have experiments to measure it. It was excluded I think 3 years ago, this band. It was a big stuff, but they remake the analysis, they make some mistakes in the analysis, so it's reopened. So you have a little window where the black hole can be full dark matter. Okay, 10 to 17, 10 to 19. A lot of people work on that, by the way. So here, before an acoustic dark matter is a product of decay, right? The black hole should be blind, right? It's gravitational object. So if it decay, it's also decay in dark matter. It's unavoidable. It will not decay in everything except dark matter. I mean, it will be your charge, except if you charge it with a charge of dark matter. You can play with a charge, and supposing black hole is charged of the solar model, but not dark matter. But normally, it's gravitational object, so it should decay also in dark matter. So this is why I say it's minimal, right? So it's possible this dark matter is light or heavy. So the zone which is low, so right recombinance is on this line. So white is okay, which means you don't overproduce. So you can have dark matter light, below temperature black hole, or heavy, because you are above the temperature black hole and you produce it when the temperature just go above the mass. Okay? So it's working. Just to show you, it's working. Okay? So you have these two regions. This one for this region here, and the yellow region corresponds to the top here. So you can produce dark matter with the right recombinance with PBH. Okay, you'll say, okay, why not? And you can combine both, because in the case of inflaton, in fact, you do the same exercise. Inflaton scattering, you exchange a graviton, and you see what you produce as dark matter. It's still gravitational production. And you can see that, for instance, for beta smaller than this value, it's the inflaton will produce dark matter. For beta above this value, is PBH will produce dark matter. So you have a line of beta where the scattering through graviton dominates because of the inflaton. But if I increase my density of black hole, I have a zone where my black hole dominates by dark matter production. So you can play this game, of course, with gravitational waves also. We have produced dark matter. I produce photon. I produce also gravitational waves. So same mechanism. So a black hole decay, this I told you can be photon, can be dark matter, can be graviton. So you say exactly the same game. So I produce graviton. So the spectrum is easy. So it's a thermal spectrum, more or less. You redshift the spectrum of the gravitational waves. You also have a thermal spectrum with the frequency I told you for 1 gram is 10 to 14 hertz. Okay, for the peak. And for the inflaton is the same. Okay, so you produce graviton also. Okay, so they oscillate and produce graviton. But the redshift, the frequency redshift this time because inflaton redshift, the frequency of graviton redshift also the production. So it's more complex. So you produce at the beginning with a given oscillation and phi, then you redshift it, you produce, you redshift, you produce, you redshift. So you can have a shape. So the shape is not important, but the shape of the spectrum is this one. You produce a lot. So this frequency here at the production is smaller because it has redshift more, of course. And of reheating, it is there. Frequency larger because you have less redshift, of course, but less gravitational waves because inflaton has less, it has diluted. Easy to understand. Okay? So if you have an inflaton which is radiation, it's a little bit particular. If you have a pressure which is 1/3, because in fact, I produce at a frequency, right? I'm diluting the frequency and I produce at the frequency here, which is the same dilution that the frequency I produce there from there. So it's one frequency, in fact. It's a peak, right? It's monochromatic, right? Because I produce at a frequency, my frequency is diluted by 1/A, but my frequency I produce is also diluted by M minus A. So I produce at the same frequency that the one which has been produced before, which is diluted. So I always produce the same frequency. So it's just a peak. Okay? I produce at a frequency, I produce at a frequency which is diluted here, and the one I produce is exactly the same frequency that I produced there. So I just, of course, you have different modes, these correspond to different modes, because you have n multiplied by frequency, so you have different mode because it's not exactly a cosinus function, but you can show that. So you see that you see the spectrum is very different, and you can do for K-6, which is an equation of state of 1/2, it's the opposite, because in fact it's a little trick, but the frequency is diluted more than the frequency I produce is diluted more than the frequency I produced before. Right? It's diluted like 1/A, but I dilute like 1/A squared, for instance. So I produce the frequency less, So the spectrum is inverted. So you see that the shape of the spectrum for the inflaton depends on the equation of states, but you can combine both. That's what we did. And if you combine both, okay, this is complicated because you have to use Black Hawk, a lot of codes, because of course this is just with the hands, but you have to use a lot of codes to compute it. And this is a two peak. You can see two peaks, right? A peak coming from the inflaton here, for instance. It's for a different equation of state. Huh? A peak from the inflaton and a peak from black hole. So that's the kind of shape you can expect from the natural waves if you have black hole plus inflaton. Okay, you can also Bremsstrahlung graviton, of course. Graviton can be Bremsstrahlung by what you produce. This is also a game we did. So this is another way to produce that matter. And you can do Bremsstrahlung if you produce a heavy right-hand neutrino, for instance. Here you can produce also graviton from the Bremsstrahlung, which is also interesting, which has been made by Choi et al. Just recently, 6 months ago. So you can always play with the Bremsstrahlung. So you have a lot of ways to produce the gravitational waves, okay? And before concluding, okay, I still have 5 minutes. Yes? Very good. So you can also produce right-hand neutrino, right? I told you can produce photon, you can produce dark matter, you can produce graviton, you can produce right-hand neutrino is gravity, so you can produce whatever you want. And right-hand neutrino is good for litogenesis, biogenesis coming from litogenesis. So same diagram, inflaton scatter, you exchange the graviton, you produce right-hand neutrino, or PBH with decay. You play the same game, so you know the region where there are either right litogenesis or biogenesis through litogenesis. This region is nice, is allowed. So you need a mass of right-hand neutrino of around 10 to 13 GeV and a mass of black hole less than 10 grams. I know it's very restricted, so it's not working so well, I would say, but still working. You can explain the biogenesis through decay of PBH. And the same, if you add this one, this is blue, you see it does not depend on the mass of black hole, of course, because there's no black hole here, so it's horizontal. The only dependence comes from the fact that you use the dilution. From dilution, black hole is dominating the universe, so it's the factor of dilution. So this shape which being like this is because it's diluted more and more. Okay, so it's just the effect of dilution of black hole. So you can have a right with a inflaton through graviton, you have right electrogenesis in this region. So you can in both regions you can play the role. You have right electrogenesis from the black hole or from an inflaton scattering through exchanging a graviton. Still gravity, huh? I just use gravity, huh? Only gravity. I don't need more, in fact. And some remarks, and I will conclude on this remark, in fact. Only one important remark. It's about the inflaton, the work we did with Marcos, and Marcos is much more specialized than me on this topic. But I told you it was a condensate inflaton. I always show you is something oscillating, transfer particle, but it's a little bit more complex than that. We love to be so easy. But the question is inflaton a particle or a condensate? This is valid exactly between ALP and action. Sometimes you see ALP, action like particle, or you see action, and a lot of people sometimes confuse both. Misalignment mechanism, for instance, is action, but you have research of action like particle at CERN. So it's not the same. Huh? Action, the only common point in both, it is a coupling with the matter, but it's not the same thing. So what we call a particle, it is inflaton, which is in fact inhomogeneous and produce particles through the decay. That's a particle will decay into dark matter or right-hand neutrino or gravitational wave, whatever you want. A condensate is a particle which oscillates, okay? Homogeneous, okay? With temperature, as I say, boson chain condensate. Temperature is 0, you oscillate, you produce particles through the oscillation. So there is a way, because in fact you go from one to the other one quite easily. So mathematically speaking, what it is that when my inflaton will produce particle, it will produce a little bit more particle here than there, because my inflaton is not completely homogeneous, right? There's a little inhomogeneities of 10⁻⁵. So we'll have more particle here than there and more here than there. So the particle I will produce, in fact, will not be localized, will be localized, right? Will not be homogeneous. I will create particles, quanta. Okay? So the quanta will destroy my condensate. This is called back reaction, right? Which means this is my equation of motion for chi. It depends only, in fact, normally on time, right? But if I add a particle, which is chi, okay, well, my coupling with phi square chi. So I will have a chi will depend on the position. And so the dependence on position will be reflected on my evolution of phi over chi because it's the same coupling, right? So if I have a coupling between my field and another field, my inflaton field produces particle, which is in fact has a dependence on the position if you want. it will change my equation of phi, and my phi will begin a particle. Okay, just roughly speaking, to see what's happening. Okay, so you have to solve this equation. So it means more or less that I begin with a phi which oscillates with the frequency m phi. I can imagine that this field, in fact, I cut it like this, right? And in fact, I have n particle. I can suppose it's n particle who oscillates, okay, with a frequency omega phi. I can imagine that. It's the same. Okay, I said this is n particle, and I consider the particle, n particle, which all oscillate together, right? I can do it. So n coherent oscillators. But if I create particle with different momentum, each particle will back react on my field, on my inflaton field, and you see that the frequency will change. Okay, and so I will destroy my condensate because each particle will attack will have a different frequency, and my condensate will begin to oscillate differently depending on my place of space, and I will begin to form a particle. Okay, this is the destruction of the condensate. So this is an incoherent oscillator of a mean momentum. So the mean momentum doesn't change, but it's incoherent. So how you see it when you code it? Okay, this is made with Cosmolitis and with Marcos. So if you begin. So this is the condensate part of the inflaton and the particle part of the inflaton. Okay, different colors at the beginning, and then red is the sum of both. At the beginning, my field is pure condensate, right? And this is my scale factor. So after 10-fold, so after my universe is 10 times larger, 10-fold, which is e power 10, depends on the convention or log, you see that my inflaton begin to form a particle, right? Because the particle which is produced, in fact, begin to attack my own condensate, which begin to be a gas of particle. That's very important because now it's a gas of particle. M-4, it's like a photon, right? I transform a condensate, which was like a matter field, to in fact, it doesn't work for Kegel too, but I transform a condensate into a particle. Okay, and that's very important because what we show with Marcos very recently, it is that you can have even the phi which can attack itself. Because phi also some little perturbation, okay, delta phi. And so the delta phi, the perturbation of phi can in fact itself attack phi and destroy the condensate. So the condensate itself can self-destroy itself by self-interaction. Okay, of course, it happens much later because the coupling is much weaker than the one I took before. So you need 50,000, for instance, between A and AN. But you see the equation of states is going for 1/2, which corresponds to K=6, to 1/3, which is a gas. 1/3 is a gas. Huh? So I have a condensate, my equation of states transformed into a gas. Okay, so I destroy condensate to a gas. So this is just some subtleties I wanted to tell and to insist, because when you treat an inflaton, you have also to check that it doesn't destroy. So I will skip the spectator of that matter because we have a lot of time, I think. How many left? I have how many left? See? 2 minutes is okay still?
Yes.
You're not too tired?
No.
Sure.
We're sure.
Okay. So this is very recent, what we did with Marco just what, 2 months ago? So it's super recent. There is another kind of dark matter which is also gravitationally produced, but not it changes the graviton, just using what I told you at the beginning of my talk, using the fact that you can create a condensate with a h⁴, remember? Yes, h⁴ doing inflation. So what's happening is that if you have some perturbation in the universe, so before inflation begins, when inflation begins, my perturbation, this is I represent perturbation with a spectator field, which means a field that does not interact with other particles, is a spectator of the universe. My perturbation will be stretched by the expansion of the universe, okay? And so my perturbation will go out of my universe. This is the horizon, it's where I live. I have an inflation, right? So I stretch my perturbations. They go out of the horizon, so I don't see any perturbation anymore, right? It's a constant field. It's not oscillate anymore. It's far away. But after inflation, during inflation, my universe increase, and after inflation, my universe increase, right? My Hubble rate increase. So my Hubble rate, so this is at the end of inflation. My Hubble rate will increase, and little by little, you will catch again my perturbation, and I will see my perturbation coming again in my universe, right? So I will see my perturbation, which was before inflation, coming back to the universe now. So we call exiting the horizon and re-entering the horizon. Okay? So what you exit at a given time, re-enter later. Right? During reheating, they re-enter. Okay? That's very important. So if you do mathematically, it's quite easy. I have this equation of motion. The only difference with QFT, it is I have the expansion rate here. If not, it's exactly the same. Okay? You see that if my Hubble rate is very large, right? Sorry, if my Hubble rate is more than the mass, very large, you see, my equation is chi equals constant, right, is a constant field. I'm outside of the horizon. Okay, constant. Then my Hubble rate will decrease. My mass will be larger. When my Hubble rate is less than my mass, I'm in an oscillator. I oscillate, right? I'm constant, like the inflaton field. Same. I'm oscillating. So when my Hubble rate will be at the size of my frequency, I oscillate. Easy? Right? Outside, I'm constant. Hubble rate equal m. I re-enter. Bam. Right? My Hubble rate decrease, my horizon increase. I catch my mass. I oscillate. So I will begin to oscillate and I will begin to form matter field, oscillating. Okay, so you see that and of course, my density is very easy. I told you before, is my Hawking-Gibbons temperature, which is h to the 4. Remember? First slide. Easy, huh? So I produce dark matter. Very easy. So this is what they call spectator field. It's a kind of dark matter. It's like the action. Huh? It's the same idea of action. If you think as action, it's more or less the same idea. Okay? So that's what's happening. It's the same. So I have my phi will decay, will radiate. That's what we know. But you can have my chi, which is out of the horizon, is constant. Remember? Out of horizon is constant. I don't have the mass. My horizon increase. I re-enter the horizon. I achieve like a mass. Okay? I'm like the inflaton field. Right? So here, I follow the same law than here. Right? Both have the same behavior. And it's a dark matter. Okay? And of course, you have to be careful. And this is my density, which is just the same that I had during inflation, but restricted by the fact that my universe expands, so I dilute. So of course, you have to be careful. And this is a right recommendation. Easy? Okay? Radiation, dark matter. I should have 10 to minus 5. And of course, you should not have that. Because of course, if you re-enter the horizon after dominating the inflaton, you have a phase of inflation here. Right? Constant density. So you have inflation, reheating, and then you begin to accelerate again, which doesn't correspond to what you observe. So it's forbidden. We'll give you a limit on the mass. The mass should be more than something because you should re-enter earlier. Okay? You can also re-enter before, okay, there, but it's forbidden because you enter too late. Right? You're not a phase of inflation, but it's too late. So your density is too large. So it's better to re-enter here. Right? If you want to re-enter here, bam, my density is very good. So in fact, the mass is fixed by when I re-enter my horizon. Easy? I don't have parameter, yeah? I just have gravity. I just have h to the 4. I have nothing else. I have h to the 4, I know h. I have the mass. So I just have the mass as a parameter, that's all. I have nothing more than my mass. Okay, and this is the recombinance you have. So you have the temperature you need, and the mass you need to have the right recombinance. Okay, and of course, if my phi field is not dust, but as a pressure, it's even worse, because you see that you have over density, because my phi gives a temperature which is very low. Okay? You have the same kind, you heard about curvaton? Curvaton, you know? Curvaton is the same as that, but it decays into photon. So curvaton is exactly the same story, but it's not dark matter stable. It has a coupling with standard model, and it reads through its decay. Okay? So that's what we call spectator dark matter. And of course, if you include PBH, it was the M, and this is my last slide. You can do the same, but if I have here another perturbation which is larger than this one, over to the critical, okay, you can understand quite well that when my universe will expand, when you will catch this perturbation, the perturbation will collapse and will form a black hole. Okay? So this is spectator dark matter, but this my spectator dark matter has the perturbation larger than my critical, it will collapse. So some part of my dark matter, proportion of my dark matter, will collapse to form black hole. So the same source will give you the dark matter and the PBH. Right? And so you can play the game, and of course, in this case, so you have this which is working, I'll show you, and the PBH can here dominate the universe, same story, it can decay, formed by the same perturbation, and if it was too much recombinance, now it can be okay because I decay after. So you can play on the game. This was my last slide, and you can play on all what is necessary. So I will conclude, because it's not so necessary between isocurvature and curvature is not important. So going further, I told you because I developed, so as I say, in leptobiogenesis, This I explain you, so it's okay. As I say, graviton is working also. You can do burden effect for Bailey. It's quite recent. It's valid. We wrote the paper 4 months ago. When I wrote the equation of black hole, evolution of black hole, right, is m Planck 4 over m black hole square, okay? But in fact, this is guess, right? The idea of Valley, it is what we call back reaction. This is entropy. In fact, when a black hole radiates, the product of what you produce can back react and forbid your black hole to evaporate. So it renders the lifetime much longer, right? It's not an explosion, it's something much soft. Okay, you have something soft. You produce, but you reabsorb what you produce. So when the temperature of the black hole is at the level of the mass of the black hole, which means when half of the mass has evaporated, your product of evaporation will back react from gravity to yourself. And the black hole will not decay, or much lower. Okay? So it's not bam, like in Hawking paper, it's boom, boom, like something will go down. Every time you have half of the mass, you back react and you slow down. Half of the mass, back react, you slow down. Half of the mass, back react and slow down. So it's like steps. So this changed completely the parameter space. When I told you 10 to 17 GeV, it becomes now 10 to 6 GeV. All the black hole has a longer lifetime. So before I told you 10 to 17 gram is lifetime of universe, now it's 10 to the 6 gram, which go to age of universe. This is still in discussion because, of course, it's 1 over the entropy, power, whatever you want. In fact, it should be a function of entropy. Nobody knows what is this function of entropy, of course, but it's just an effect to mimic the back reaction effect. This not coming from black hole. The paper of Valley is just be applied from an information theoretical paper about conserving information. It's I don't know at all about conserving information, but it was a way to solve the information problem of black hole, right? Which is applied to the lifetime of black hole. It's just because when you lose information, you recover information you are losing through the entropy. It's a complex field, so I don't know more than just I told you, because the paper of information is complex. But phenomenologically speaking, it's just telling that if I produce entropy, I slow down the decay of my black hole. And you have also something I didn't discuss about Kerr black hole. My black hole was not turning. If I make my black hole turning, change what I told you, okay, because you have some effect of spin, okay, of the black hole. And so you can produce what we call super radiance. You can produce much more particles by spin conservation because you can turn much faster, right? Like spin is something which is spinning like this, right? So if you produce particles with spin, in fact, the black hole can spin more and more and more and decay very fast because spinning will act the decay more. So when the black hole is half of its mass, the spin will act a lot of its lifetime. But I didn't discuss this in this paper, but we are doing now the same plot with a spinning black hole. Conclusion, easy. PBH can read, Iflation can read, P calculates, Inflation can, PBH can, Inflation can, PBH can generate, Inflation can also. So gravity is cool, right? So that's all. Thank you very much.
Excellent talk. We're open for more questions now.
Yeah.
Thank you for your talk. I was wondering if, since you can have similar results from both the scenarios, is there a way to, from measurements, know whether things were driven by inflatons or by black holes?
Yeah, it's a good question. As I say, gravitational waves, for instance, because the spectrum is very different, the shape of the spectrum, as you say, it's almost the same frequency, but the shape of the gravitational wave is different. Unfortunately, what's happening? Reading is the worst thing you can imagine because the reading means all the past is erased by definition. I have any kind of particle, I put it in my key room, you don't know what was before. I mix blue and red, I put a glass of water, I mix all, I cannot go back as what it was before, right? Just the story is forgotten. So the only, I would say, it's sad to say that, but the only particle which does not care about that is a graviton. It doesn't care about reading, it doesn't interact, okay? You can say neutrino, but neutrino is 1 second only. So it's not what we want. 1 second is a decouple of 1 second neutrino, right? 2 MeV more or less. So neutrino is good between 1 second and CMB as a good mediator because it does not interact. So neutrino keeps the story between 1 second and 380,000 years. So it's good. So that's why C mu B is important because it will give us all this information that it doesn't share with the photon. But of course, from inflation to now, the only particle I know which doesn't care about the photon is a graviton. So I think if you want to distinguish all what I told you is gravitational waves. So that I think that's why you have so many papers on that. I mean, I think you go spy, we have 5 or 6 papers on gravitational waves every day. Second reason, of course, is we discover gravitational waves. We have to admit it, so it exists, okay, which is a good point. And third, okay, on my point of view, you look at CERN and you have a lot of projects for resonant. I didn't discuss about it. Is resonant cavity. Don't forget that the experiments which was aimed to discover gravitational waves, like future Einstein telescope, LISA, etc., was made before all these new things about gravitational productions, more or less. So the aim was to make big experiments, right? Because you want to have big wavelengths, right? Small frequency. You want to see supermassive black hole colliding. So you need something like 2 million kilometers for your interferometers. Einstein telescope also is very large. Okay, so that's natural that the experimentalists went to huge laboratory to measure, and it's important to measure that, right? Or stochastic gravitational waves. Okay, that's important, like PTA, okay, pulsar timing array. That's important. Okay, but now you have a lot of projects about small, because 10 to 11 hertz means, of course, small resonant cavity. I read some projects. I'm not specialist on that, but I can tell you in Paris, in France, you have 3 or 4 projects on that, working on that. At CERN, you have 2 projects on that. A lot of people want to work on that. So I'm quite optimistic that in the future generations, not me, I will be a Chinaman, your generation, a lot of young here, okay, you will be able to discover this. Because, as I say, it's not only for the history of black hole. I mean, we say who care about PBH. It's just that having information about the primordial gravitational waves give you information about the history of the universe, more or less from the end of inflation. So that's huge. You have all the history of the universe. Imagine the spectrum you have. You have to, from 10 to minus 38 seconds to now, you know the history of the universe. So I think, so the frequency we have now is 1 hertz for PBH, like Virgo, 0.1 hertz, 10 to minus 3 hertz for Einstein telescope, which is more for supermassive black hole, or 10 to minus 6 hertz. To go to what, 10 to the 10 hertz. Okay, you have a lot of projects, not yet. What I heard, I'm not specialist in my lab, they want to do that also in IJCLab. It's a single photon. I'm not all, I'm telling just what I heard. It's a single photon. You have more or less, you have a photon, a resonance, you have a photon. Okay, you interact with gravity. Okay, so you change the things. So you have H mu, F mu if you want. So you see the change of frequency because you interact through gravitational waves. And gravitational waves passing, you change the frequency and you have a resonance to know the wave. So that's more or less what it is. So you have to have 10 to the 11 hertz. You want to have resonance with the graviton, and then you see graviton passing. That's the idea. But the thing is you have to measure 1 photon, right? So it's called single photon problem. And this is super hard. So the technologically, I think what I heard technically, they are stuck because, of course, you have temperature everywhere here. So to have 1 photon, single photon, because even theoretically, I think with the Heisenberg principle, you can easily show that to see 1 photon is impossible. I think it's very complicated. But once you solve this, I think the technology would be able to see that. The limit you have more or less I show you. So I give you some numbers. It's not important some number. So what we observe should be is omega gravitational waves is around. We expect around 10 to minus 15 to 10 to minus 10 when you are very optimistic. The prediction of the nowadays gravitons is 10 to minus 8 with the now technology. We optimistic 10 to minus 10. So you can easily see that you need, I would say, 5 to 10 order of magnitude in the new experiments. And this you can check. But it's interesting because you can make a paperwork, omega gravitational waves. You put H to the 4, you divide by temperature nowadays. You will see that more or less you get 10 to minus 18. So you know, whatever is your model, it will be some shifts, of course. Some will give you that. But between 10 to minus 18 to 10 minus 10, you have 90% of the model. So my point of view is that.
More questions?
And of course, CMB polarization. Oh, this didn't discuss this, but of course. So when the light bulb should measure CMB polarization, so graviton polarized CMB. So it's an indirect way to see graviton through the polarization of CMB.
Yeah, because as another piece to the same question, is there a potential for the platon that can mimic the primordial black holes?
No, because they are very different objects. Yeah, no, they are very different objects. The lifetime is different, etc. Before waiting, no, they are quite different because one is a constant. I believe you think about something else. I think about in laboratory, like you do, how you say, you mimic gravity, or the name of the science. When you mimic gravity in lab, with waves. There's his name. Forgot. I lost my memory. You mimic gravity with waves. You know, you mimic black hole with waves.
Yes, yes.
Analog gravity,
Yeah.
right?
Yeah.
When you make analog gravity, you make ferrogravity, you make energy with waves. Probably within Platon, you can do the same in quantum mechanics. I'm supposing what you see within Platon is a Bose-Einstein condensate at the end. Probably you can mimic it in quantum theory. Right.
Thank you.
More questions?
Thank you for your talk. Can gravitational waves be produced by merging primordial black holes?
Oh, yeah, some people look at that. Yeah. Even in your universe. Yes. I saw some papers about that. Yeah, merging primordial black holes in a universe. Yeah. It's a as I say, this science of primordial black hole in a universe, because it's not more about the formation now, it's not the evaporation. Because as you say, evaporation is quite easy, it's classic, it's a 74. So binaries is quite new. Okay, formation of black hole in the universe is also new because now you have computing tools to do that. It's quite complex. And I heard effectively, I see a paper where they try to find a binary collision of the black hole. Okay, yeah, that's could be interesting also. But I'm sure it's super complicated. Much above my level.
More questions? No, not. We thank Yann for next one.
Thank you. Next week. 222 the office, huh? 222. If you want to discuss,
Yes,
222.
no, please, 222. So you'll be here.
That's
Please go on asking things.
Thank you. Have a nice day. That's okay.
Right?
Yeah.